Well, David, thank you for those very, very kind comments, and I certainly hope the lecture I'll give today lives up to them. What I want to speak on today is really about insulin resistance. Most importantly, what it is, because most people really don't know, including at the really the higher levels of academic research. But once we describe that, then showing what you can do to actually reverse it. Oops. Okay, there we go. Well, even though insulin resistance is very complex, we know of the complications of insulin resistance. Obesity is one of those, but the most drastic one, the one that really threatens to destroy our entire healthcare system, is diabetes. And this is what is really the number one focus of American healthcare should be, is saying, how do we reverse our diabetic epidemic? Because as that increases, that will lead to a corresponding increase to a wide number of other chronic disease states which can be traced to insulin resistance. So in the course of the lecture, I'm going to try to enumerate several goals. The first is asking, what does actually insulin do? A second is trying to discuss insulin resistance. Thirdly, talking about the causes of insulin resistance, asking where it starts, what might be the underlying dietary cause, and finally, how best to reverse it. So let's start with the first question. That is, what does insulin actually do and how does it work? This slide kind of summarizes our knowledge of insulin action, which says there's a lot of question marks in here. We know that insulin interacts with the receptor on several target tissues. And once it interacts with that receptor, something happens in the cell. That's a big question mark. But during that something happening in the cell, we get a biological effect. So it's what's the difference, what's happening between the receptor interacting with insulin and the biological effect is where we can search now for what is really insulin resistance and what's actually causing it. But before that, let's ask what insulin actually does. Well, in terms of, it does many things in terms of primarily controlling your metabolism. In terms of carbohydrates, it's key for the synthesis of glycogen in the liver and the muscle. It also inhibits glucose synthesis in the liver. So you're already beginning to see kind of a yin-yang type of approach that in some cases we build up glycogen, in other cases we decrease synthesis of glucose. In fats, it promotes the synthesis of fatty acids into triglycerides for storage in the fat cells. Likewise, it inhibits the release of fatty acids from the fat cells. Again, this yin and yang type of principle. And finally, it's important, it's critical for the synthesis of amino acids in the protein via a nuclear transcription factor known as mTOR. So you can see from this very simple slide, there is no part of what we call metabolism that is not ultimately related to insulin and insulin working effectively. And when insulin works effectively, it gives us what is called metabolic flexibility. What this means is we're able to orchestrate the use of different fuels by the body. It allows us to switch from one fuel to the other, fats to carbohydrates and vice versa, and also basically where we basically pull that energy from. Is it pulled from the adipose tissue? Is it pulled from the liver? Is it pulled from muscle cells? So having insulin working effectively gives us great flexibility to manipulate our metabolism to maximize our output of ATP we need for energy and survival. Now we can talk about the academic definition of insulin resistance. And usually when academics talk about insulin resistance, we try to put in such, god-awful terminology that nobody understands what it really means. So here's how we would define it academically. The target tissues become resistant to insulin action. The target tissues could be the adipose tissue, it could be the liver, it could be the muscle cells. However, a far better definition of insulin resistance, in my opinion, is something like this. Something has gone wrong in the cell. Somehow, something between insulin interacting with the receptor and insulin doing what it's supposed to do has gone awry. And when it goes wrong, we get sick. Why is that? Because insulin is the primary regulator of metabolism. Now, to show you the complexity of what goes wrong, here's a simple, actually very highly simplified diagram of how insulin interacts with the receptor, and when it does, what takes place. And as you can see through the slide, a lot of things take place, many of them ending up in causing genetic transcription in the nucleus. Any one of these steps can be somehow inhibited or corrupted, and if so, we get sick. That's what happens when we get insulin resistance. Now, we talked about some of the insulin responsive tissues, but there are more. The adipose tissue is one, the muscle, the liver, also the kidney, and surprisingly the brain. But that's a yes and no. That glucose does not require insulin to get into the brain. However, insulin can get into the brain to act as a satiety hormone. So, in some ways, insulin has no effect on blood glucose transport into the brain, but it has a very, very great impact on hunger and satiety that helps us maintain that metabolic flexibility. So let's go to the second goal of the lecture of what really causes insulin resistance. What happens when basically something goes wrong in that very complex pathway I described earlier? Well, there are two competing theories right now for insulin resistance, or what causes it. But in many ways, and I'll try to explain later, I think they're really two sides of the same coin. The first theory talks about lipotoxicity. It's kind of finding love in all the wrong places. There's only one cell in the body that can store fat safely, and those are fat cells. But when fat begins to migrate to other cells that don't have that storage capacity, bad things happen. And one of those bad things is called insulin resistance. The other competing theory is inflammation. Somehow those signaling mechanisms that give rise to those complex interplays are being inhibited by inflammation in the cell. So let's look at the lipotoxicity mechanism. And in this particular mechanism here, you find fats going into the cell. It could be a fat cell, it could be a muscle cell, but somehow you're making more of what are called diglycerides. And these diglycerides cause basically lots of problems. And primarily, the problems end up inhibiting the action of insulin with its receptors. Now, these diglycerides, they come from either incomplete hydrolysis or incomplete triglyceride formation from fatty acids. Fatty acids by themselves are very toxic. Fatty acids by themselves are basically soap suds. They act as surfactants. They cause things to dissolve, like red blood cells or the cell membranes. That's why the body goes to great lengths to take fatty acids, which are incredibly dangerous and toxic, and put them into a safe storage form. That storage form is called triglycerides. But if that step is somehow inhibited, then you'll get an accumulation of one of the byproducts of this triglyceride formation called diglycerides. And what these diglycerides do, they inhibit the translocation of the GLUT4 protein to the surface of the cell so it cannot pick up glucose and bring it into the cell. Furthermore, these diacylglycerols activate what is called protein kinase C, which again gives rise to a whole series of problems, giving rise to basically breakdown of insulin signaling. Along with this is another area of where lipotoxicity comes from, and that is the increased formation of what are called ceramides. Ceramides are really the key component that forms lipid rafts. And these lipid rafts can either inhibit or enhance hormonal signaling. In the case of insulin signaling, they basically cause a decrease in that. So somehow, that one competing theory of what causes insulin resistance is that the lipids are not being completely transformed into triglycerides, or there's an increase in ceramides, but in either case, the end result is something goes wrong in the cell, and that's what you call insulin resistance. On the other hand, the inflammation theory of insulin resistance is quite different. Here we're looking at various inflammatory mediators. They could be cytokines, they could be derivatives from arachidonic acid, but whatever they might be, they'll cause an inhibition of the insulin signaling pathways, usually going through another transcription factor known as JNK, or also another one known as nuclear factor kappa B. But like I said, even though these seem to be two competing theories, in many ways they can be considered two sides of the same coin. Now, in many ways, we talk about inflammation, we can take a much more wide scope, and I've talked about this in previous seminars here on building strength, talking about inflammation as really a secret killer. And here's a Time magazine article several years ago describing this, talking about the surprising linkage between inflammation and diabetes, heart disease, cancer, and Alzheimer's. These are all diseases of inflammation. And that's why, in many ways, the inflammation that causes insulin resistance is also the beginnings of these chronic diseases. So exactly what is inflammation, if it's so important? The ancient Greeks tried to describe it as the internal fire. The ancient Romans described it as heat, pain, swelling, redness. And frankly, that's how most physicians still describe inflammation. In fact, if a patient asks a doctor, what's inflammation? Usually the doctor will say, it's very, very complex, which is simply medically shorthand for saying, I don't know, I just know it's bad. But we do know that inflammation is usually associated with pain. Something hurts, and that's why you go see a physician. But we know that pain is mediated by a distinct group of hormones called eicosanoids. How do we know that? Because virtually every anti-inflammatory drug known to medical science, whether it be an aspirin, a non-steroidal anti-inflammatory, a COX-2 inhibitor, or even a corticosteroid, works by only one mode of action: to inhibit the formation of eicosanoids that cause pain. Now, we have to have an inflammatory response in our body. If we didn't, we'd be a sitting duck in a very hostile world. We'd be an easy target for microbial invasion. If we did not have inflammatory responses in the body, we could have injuries that would never heal. And this is the primary reason why inflammation is so critical to our survival as a species. But we know that besides microbial invasion turning on inflammatory responses, or injuries turning on inflammatory responses, something else, only recently discovered, can also turn on those same inflammatory responses. And that turns out to be our diet. As we've conquered microbes, we have less injuries. What's taken the place of those two factors has been our diet, and a rapid change in our diet that is now turning on inflammatory responses 24/7. And with those increase in inflammatory responses comes an increase in insulin resistance. Now, we talk about inflammation, but there are two types. The first type is called what I call screaming pain. This hurts. This is when you have organ or joint damage, and you say, it hurts, you see a doctor. But there's a second type. This is what I call silent pain. This is the type of inflammation that Time magazine article was describing. A better way academically to describe this might be cellular inflammation. Inflammation at the cellular level that's below the perception of pain. And since there's no pain, you do nothing to stop this type of inflammation, meaning it can linger for years, if not decades, until there's enough organ damage that we call it chronic disease. So this inflammation, the cellular inflammation, it is without pain, but we now know it's induced by the diet. And how it's induced by the diet is explained in this very simple diagram. This actually describes the most primitive part of our immune system. It's called the innate immune system. It's the type of immune system that we share with plants. But it's primitive in that it's based on pattern recognition. The key part of this whole innate immune system really lies here in nuclear factor kappa B, because this is the genetic master switch that will turn on inflammatory responses and amplify them by causing the nucleus to basically now give greater transcription of enzymes such as COX-2 or cytokines that can basically spread the inflammatory signals to nearby cells. So let's make that diagram a little simpler. We have several ways that nuclear factor kappa B, shown here, can be basically turned on. One, cytokines from other nearby cells can interact with their receptors and send signals that basically activate nuclear factor kappa B. We can have toll-like receptors, which are activated by saturated fats in the diet, activate those toll-like receptors, and that turns on nuclear factor kappa B. We can have arachidonic acid, an omega-6 fatty acid in the cell, being transformed into leukotrienes, which also turns on nuclear factor kappa B. And when nuclear factor kappa B is turned on, out comes a wide number of inflammatory enzymes like COX-2 or inflammatory cytokines like interleukin-1, interleukin-6, tumor necrosis factor, and a wide variety of others. But there are other transcription factors in the cell, such as PPAR gamma, that can actually turn off nuclear factor kappa B. So you see, our innate immune system has a very, very sophisticated on-off system to control inflammation. And most of those control points, as I'll describe later, we can basically manipulate for better or worse by the diet. Now, these transcription factors, which were all but unknown a few years ago, are now at the cutting edge of molecular biology. There are pro-inflammatory transcription factors like nuclear factor kappa B, as I said earlier, activated by leukotrienes derived from arachidonic acid, but they can be inhibited by omega-3 fatty acids, and they can also be inhibited by polyphenols. Polyphenols are simply the chemicals that basically give fruits and vegetables their color. That's why the more fruits and vegetables you eat, the healthier you are, because what you're doing is managing and reducing cellular inflammation. The same is true about omega-3 fatty acids. The more omega-3 fatty acids you eat, the healthier you are. But there are, as I said earlier, there are also anti-inflammatory transcription factors like the PPARs. These are activated by hormones in the fat cells, particularly adiponectin, but they're also activated by omega-3 fats and by polyphenols. At this point, you're hopefully beginning to realize that if your diet is low in omega-3 fatty acids, or low in fruits and vegetables, and therefore low in polyphenols, you're putting yourself at great risk to increase inflammation at the cellular level. And if you do this, this will now increase insulin resistance in every cell in the body. Now, these inflammatory mediators associated with insulin resistance we can pick up. Things like inflammatory cytokines. I said tumor necrosis factor, interleukin-1, interleukin-6. We can add interleukin-8, interleukin-13, interleukin-15. Right now, there's something like 37 different interleukins known, and they're all having different inflammatory effects. But these are derived not from fat cells, but derived from activated macrophages in the fat cells, which are turned on by inflammation. Likewise, the activation of nuclear factor kappa B can be activated by leukotrienes derived from arachidonic acid, but I'll make it even simpler. We'll call arachidonic acid toxic fat, because in high levels of arachidonic acid, it is toxic. In fact, early experiments done back in 1975 demonstrated that if you inject virtually every fatty acid known to man in the rabbits, nothing happens. If you inject cholesterol in the rabbits, nothing happens. If you inject arachidonic acid in the rabbits, they are dead within 3 minutes. That's why I call it toxic fat. Now, in terms of insulin resistance, there actually have been some miracle treatments for it over the last 2 centuries. In the 19th century, specifically in 1876, that's almost 150 years ago, it was found that high-dose salicylic acid could reverse diabetes completely. But salicylic acid was incredibly bitter tasting. And even though it was an anti-inflammatory agent found in things such as willow bark, until it was learned in 1899 how to take the taste out of salicylic acid, by making the acylated derivative. We call that aspirin. In the 20th century, there are numerous reports that diabetic patients taking high-dose aspirin, about 5 grams per day, were seeing remarkable reductions in their blood glucose levels. A wonder drug, incredibly cheap, but at 5 grams per day, potentially very toxic. Now let's go to the 21st century, and in 2002, in the Journal of a Clinical Investigation, it was found giving aspirin to type 2 diabetics at the level of 7 grams per day gave rise to a 25% reduction in their glucose. A massive amount of aspirin, but a very significant amount of reduction in glucose in a very short period of time. Again, indicating that insulin resistance, the hallmark of diabetes, may be an inflammatory disease. Today, they have studies ongoing throughout the world with an old variety of salicylic acid. It's a dimer called salicylate, and at very high levels, it can act as an inhibitor of nuclear factor kappa B and give about a 50% increase in the uptake of glucose, which means you're reducing insulin resistance. So now we go to the third part of the lecture of asking, where does insulin resistance actually start? We have many tissues in the body that are insulin sensitive, but where does it actually start? In my opinion, and the opinion of many others, it actually insulin resistance for a wide number of other basically staging areas to really deliver inflammation throughout the body. The reason why I'm very strong in that aspect, this is a recent study published in 2007 in the Journal of Clinical Investigation, saying here's another way of reversing diabetes. The rat here on the right-hand side was an obese, diabetic rat. What they did to these rats was then to place in them a transcription factor, or basically an increased expression of the hormone adiponectin. Remember, that's the hormone made by fat cells. And what you saw is these fat rats became super obese, massively obese, but with a complete disappearance of all of their diabetes. The diabetes was eradicated completely, even though the rats became super obese in the process. What was transpiring is that fat cells, which were inhibited by insulin resistance, new fat cells are being made, which were healthy fat cells. And what they could do, they could suck out all of the fats from the other tissues and bring them back into the fat cells, and with that, complete relief of diabetes. In my newest book, Toxic Fat, I basically talk about this in much greater detail because it gives a new understanding of cellular inflammation and what it is, and more importantly, how we can reverse it. Because there are really 3 types of fat. There's subcutaneous fat. These particular fat cells are ones which are healthy fat cells, and as a consequence are the ones that can pull out toxic fat from the blood and basically bury it like a toxic dump. The second type of fat we can call bad fat. This is the visceral fat. This is the fat that accumulates around your midsection. And we've been led to believe that that is simply an indication that's where all the bad results come from. But it turns out visceral fat really has no impact on diabetes. There's an association with diabetes, but it turns out there's no causality because you can surgically remove from obese diabetics and find that they'll have no impact, positive or negative, on their diabetes. But there's a fat of the third kind. I call this malignant fat, just like a malignant tumor. This is where fat now becomes metastatic. It moves from the one fat cell, or the one location we can store it safely, fat cells, and begins to move into other cells which don't have that capability. Cells like the muscle cell, or the liver cell, or the heart cell, or even to the brain. And when basically the fat begins to accumulate in those organs, then we have the beginnings of chronic disease. It could be diabetes, it could be liver failure, it could be heart disease, it could be Alzheimer's. So really, we can look at now the lives of the fat cell from a new perspective. If you have good fat, then your fat cells are very healthy and they can do what fat cells are supposed to do. They suck out toxic fat from the bloodstream and bury it so it can't cause inflammation in other cells. Levels of the toxic fat in those fat cells begins to increase. They become sick. This is the bad fat. And what happens here with sick fat cells is that they can't accumulate fat as effectively and they can't keep it stored as effectively, so now it begins to circulate into the bloodstream. And this is the first stages of what are called lipotoxicity. And what it causes this is basically inflammation in the fat cell. And now you begin to see how the theories of lipotoxicity and inflammation become two sides of this. You have bad fat beginning to spread. You have the first hallmarks of metabolic syndrome. Not a disease state yet, but an indication that metabolism is no longer copacetic. Triglyceride levels begin to increase. HDL levels begin to decrease. You gain excess fat in the midsection. So again, you're not quite sick, but you're no longer well. And now when the fat cells start to die in the adipose tissue, they basically are now releasing massive amounts of stored toxic fat. This becomes malignant fat and now basically spreads into the bloodstream and now moves to other cells throughout the body. Just like, again, a cancer cell does. You have a primary, turns out to be metastases. And this is where it becomes the start of diabetes, heart disease, cancer, and Alzheimer's. Diseases all. Now, in the fat cell, it's unique in our body because it makes certain hormones which can only be produced by fat cells. These are called adipokines. Again, we have a lot of misunderstanding, because in the fat cells, it turns out if you have an overweight patient, nearly half the weight of their fat is not fat, but macrophages. Macrophages which have been attracted to inflammation in the fat cells caused by dying fat cells which are engorged in toxic fat. And these activated macrophages now release pro-inflammatory mediators like the tumor necrosis factor, the interleukin-6, and the interleukin-1. But they're also anti-inflammatory adipokines. Adiponectin is one. Ironically, it makes you fatter, but it basically reverses diabetes. Another one that can be made by fat cells turns out to be interleukin-10. There are a lot of bad interleukins, but there's some good ones too. And this is what we talk about macrophage switching. That if you basically have inflammation in the fat cell, that macrophages will be activated and will go after it as if they're attacking a microbe. These are called M1 macrophages, or what are called classically activated. And these are exceptionally pro-inflammatory. Yet at the same time, we can basically deactivate them and turn them into M2 macrophages, which are known as alternatively activated macrophages, and these are anti-inflammatory. And the switch that apparently turns an M1 into an M2 macrophage is sitting there on the cell surface. It's called GPCR120. That's short for G protein coupled receptor that has a molecular weight of about 120. If that receptor is activated, you turn off inflammation in the macrophages and turn off the fat in the fire, or turn off the fire in the fat. Because if you don't, what's going to happen, you'll have compromised fat storage. That you'll see that the entry of glucose in the fat cells is now becoming inhibited by insulin resistance. Likewise, the efflux of stored fats into the blood is increased by insulin resistance because now there's nothing to inhibit the hormone-sensitive lipase, which requires insulin action. And as a consequence, you are now basically flooding the body with large amounts of fat that basically cannot be picked up safely by other cells in the body. And the major consequence of this metastatic spread of toxic fat is, one, obesity. Do we have an obesity epidemic in America? Yes, we do. But in reality, we have an inflammation epidemic in obesity. Another consequence is diabetes. I showed you earlier that anti-inflammatory drugs, unfortunately at toxic levels, basically can reverse diabetes very effectively. It's also the cause of non-alcoholic steatohepatitis, really the number one cause of liver failure. We can also basically increase lipid accumulation in the kidney, giving rise to elevated blood pressure, and this is why hypertension is also associated with insulin resistance. We talked about basically the acceleration of heart disease and, of course, Alzheimer's. In many ways, you can view Alzheimer's as diabetes type 3. They are both diseases of inflammation. One's a disease of inflammation of the muscle cells, pancreas, and liver. The other is an inflammation in the brain cells. But if we have an epidemic of diabetes, this means that within 10 to 20 years, we're going to have a corresponding epidemic of Alzheimer's. And if diabetes doesn't break the bank, which I'm sure it will, then I guarantee you that Alzheimer's will. So with those happy points, we can now ask, what might be the underlying dietary cause of insulin resistance? Because if we can understand this, then we have a way of reversing it. If we can't reverse it, basically our whole healthcare system is going down to a black hole which there is no coming back from. So our question is, what really causes cellular inflammation? In many ways, there's not any one particular agent, but really a combination of three, which I call the perfect nutritional storm. The first of these has been the dramatic increase in vegetable oil consumption in America, because vegetable oils are very rich in omega-6 fatty acids, and these are the building blocks for toxic fat. In the last 40 years, our consumption of omega-6 fatty acids has increased by some 800%. Vegetable oils are now the cheapest source of calories known to mankind, and they're ubiquitous. They are everywhere. But their transformation into toxic fat and therefore increased inflammation can be accelerated by the increased consumption of refined carbohydrates. Yes, this is junk food, but it's also bread, pizza, and pasta, because all these will increase insulin, and as you increase insulin, you facilitate the driving of omega-6 fatty acids into toxic fat. At the same time, we've experienced a dramatic reduction in our fish oil consumption, because fish oil is rich in omega-3 fatty acids, which at high enough levels exert powerful anti-inflammatory benefits. All these factors first came together in America about 40 years ago, and that was the start of our obesity epidemic and our epidemics of diabetes. Now, how this all works together can be explained in this slide. We start out with linoleic acid coming from cheap vegetable oils. This is acted upon by the enzyme delta-6 desaturase, which basically is activated by insulin. This moves into gamma-linolenic acid, which is rapidly metabolized into dihomo-gamma-linolenic acid, which is then acted upon by another enzyme, delta-5 desaturase, to make arachidonic acid. But these two enzymes, they're called rate-limiting steps. They're there in the body to make sure that the levels of arachidonic acid, or toxic fat, are relatively controlled. But as our diet has increased the levels of both linoleic acid and increased the levels of refined carbohydrates, we've opened the floodgates. What we've done essentially is been like adding a lighted match to a vat of kerosene. We've seen a dramatic increase in arachidonic acid, and with that, an epidemic of cellular inflammation throughout our society. So let's make it a little simpler. Omega-6 fatty acids coming from vegetable oils, activated by insulin, inhibited by omega-3 fats, and if you don't inhibit them, you get more toxic fat, and now you've got trouble. Real bad trouble. It's called cellular inflammation. Now, toxic fat, and this is where it begins the and lipotoxicity in the fat cells. Here's a disturbing picture. It should be anyway. This is a study published last year taking rats, which are genetically identical. And they took these rats and put them into two separate colonies. For the next 3 generations, they fed the rats exactly the same amount of calories. They fed them exactly the same amount of protein, exactly the same amount of carbohydrate, and exactly the same amount of fat. The only difference, one colony got high levels of omega-6 fatty acids, and the other ones got a more normal chow. You can see after 3 generations, those who were getting the high levels of omega-6 fatty acids, and therefore the low omega-3, were grossly obese. They weren't playing computer games. They had access to the same running wheels. They weren't watching TV. They were sitting there eating the same food we've been eating for the last 40 years, getting fatter and fatter, and in many ways going through really an epigenetic changes. Epigenetics is how the diet can begin to affect genetic changes which are passed from one generation to the next. And that's what we're seeing right now. Our children in America are in the 3rd generation of being exposed to this perfect nutritional storm. Each generation has got progressively fatter. We find out all the excuses, too much TV, not enough play. The answer might be as simple as what's in our kitchen. That the kitchen is turning on genetic changes, which may, I hope they aren't, but they may be irreversible. And likewise, those same colony of rats, that those who got the high omega-6 fatty acid rats over here, you can already see by the 3rd generation, even though the diets were seemingly identical, massive amounts of lipid accumulation in the liver. This is lipotoxicity. And this is now basically the metastatic spread of toxic fat. And if we look at their hearts, you find that those who got the high omega-6, low omega-3 fatty acid diet, their hearts are engorged in fat. These are very rapid changes to happen over only 3 generations. What about humans? Well, here's some data from 2004 taking children who are otherwise normal, but what you look in their fat and look at the levels of toxic fat, they correlate very well with the amount of obesity. The higher the BMI, the greater the levels of toxic fat in their fat cells. Here's data from Harvard Medical School showing that the higher levels of toxic fat in the fat cells, the more likely a person is to develop metabolic syndrome, which is pre-diabetes. How much more? 6 times more. And here's also data from Harvard Medical School demonstrating the higher the levels of toxic fat in the adipose tissue, the more likely you are to get a heart attack. So, the final part of the lecture I want to talk about is how can we reverse it? Up to this point, it's been all bad news. Bad news that basically we may be in a canoe going down the stream toward a waterfall with no paddle. But there is a way out. What got us into this mess is diet, and what can get us out of this mess is also our diet. But it has to be an anti-inflammatory diet. And how we do this, we put it all together by understanding how our diet interacts with our genes. We go back to our innate immune system, complex as it is, and we try to simplify it. But here are our dietary controls on nuclear factor kappa B. One activator is toxic fat. If I say, wake up, if I just reduce toxic fat in the body, I'll deactivate inflammation in every cell. Is there some drug that can reduce toxic fat? The answer is no. Toxic fat is caused by the diet. It can only be reversed by the diet. But we also know, as I discussed earlier, that there are inhibitors of nuclear factor kappa B, in particular omega-3 fatty acids such as EPA and DHA, and polyphenols. So if we could somehow reduce toxic fat levels, increase levels of EPA and DHA, and increase polyphenols, we very well could be on the road back to recovery. So the reversal of the perfect nutritional storm starts with we have to reduce toxic fat. That means getting omega-6 fatty acids out of your diet. Easier said than done. They're ubiquitous in every food in America. The only way you can do it is basically prepare the food yourself. Every time you go into a restaurant, I guarantee you, you're getting a meal that's rich in omega-6 fatty acids. Why? Restaurants are there to make money, and 1/3 of the cost of the restaurant is the food ingredients. And how to reduce cost? You use the cheapest food ingredients that still taste good, and that's called vegetable oils. And you also have to reduce insulin levels. How do you reduce them? You cut back on refined carbohydrates, and you eat what your grandmother told you, fruits and vegetables. The second way to reverse the perfect nutritional storm, you have to increase the levels of EPA. Yes, we talk about EPA and DHA, but it's, excuse me. Gotta go back there. I think I do this. That's not a good sign. Hold on for 1 second. And I will go back in this direction, I hope. Oh, there we are. Well, I talk about EPA. Why? And not DHA? Because EPA has all the anti-inflammatory actions of omega-3 fatty acids. DHA is important, but not for controlling inflammation. It's important for affecting lipid rafts in the cells and for basically neural structural characteristics. But it does not do a very good job of reducing inflammation. Also, EPA increases the production of adiponectin in the fat cells. That makes more good fat and helps us pull toxic fat out of other organs. And finally, increasing the polyphenols by eating more fruits and vegetables, a further inhibition of nuclear factor kappa B. Let's see. I went the wrong direction here. Let's see. And I've done something that's probably not good here. Sorry. So it's not as hard as it appears to be. All you need is one hand and one eye to start your road back toward controlling inflammation. At each meal, simply divide your plate into 3 equal sections. On 1/3 of the plate, you put some low-fat protein that's no bigger or no thicker than the palm of your hand. And the other 2/3 of the plate, you fill it full of colorful carbohydrates. They're called fruits and vegetables. And finally, you add a dash of fat. What's a dash? A small amount. But you just make sure that that fat is very rich in monounsaturated fats. Why? Because it's rich in monounsaturated fats is de facto poor in omega-6 fats. Things like olive oil, olives, macadamia nuts, slivered almonds, even avocados. But beware of adding extremely bad fats, which are high in toxic fat, like fatty red meat or egg yolks. And if you do all this, you get what I call a zone food pyramid. That at the bottom you're eating lots of fruits and vegetables, which does 2 things. Provides polyphenols and also reduces the glycemic response to the diet. You're always eating adequate levels of low-fat protein like chicken or fish. You're always adding a dash of monounsaturated fat like olive oil. And up to this point, the zone food pyramid looks suspiciously like the Mediterranean diet. It has many similarities, but it has one major difference. That is, you cut back dramatically on the consumption of grains and starches and make up for it by eating even more fruits and vegetables. That one small difference can have a dramatic hormonal effect in terms of controlling and reducing cellular inflammation. So in many ways, the zone diet can be viewed as the evolution of the Mediterranean diet into a more hormonally correct diet to control cellular inflammation. The Mediterranean diet is a good diet. The zone diet is simply just more effective in controlling that type of inflammation induced by the diet. Now, that's just not me talking. We can look at the new guidelines, dietary guidelines put forward by the Joslin Diabetes Center at Harvard Medical School about 6 years ago. They recommend that 40% of your carbohydrates should come from low glycemic load carbohydrates. Those are called fruits and vegetables. 20 to 30% from low-fat protein, and 30 to 40% rich in monounsaturated fats, which means they're low in omega-6 fats. Surprisingly, these were exactly the same recommendations I made a decade earlier when I wrote my first book, The Zone. Actually, I called people up at Harvard, and after they made the recommendations, I said, "Great, does this mean you guys are endorsing The Zone?" They said, "No, of course not. We thought these all by ourselves." That's why they say you can't tell them much. But if you do all these dietary things, you still need fish oil, and a fair amount of it, because the fish oil, the omega-3 fats, especially the EPA, can put the fire out in the fat. And it also stimulates the production of adiponectin that basically makes new healthy fat cells, and more importantly, it's an activator of that factor, that GPR 120, that basically deactivates an active macrophage into an inactive macrophage. And just to show you the power of how these omega-3 fatty acids can affect omega-6 fatty acids, you can see that there is a kind of as you increase the levels, there's a corresponding decrease in dihomogely, a more sporadic, but definitely at very high levels, a decrease in arachidonic acid. And the polyphenols, here's the little dirty secret of fish oils. You should never take fish oils unless you're eating lots of fruits and vegetables or taking a polyphenol supplement, because you'll need those extra polyphenols to prevent the oxidation of the omega-3 fatty acids once they enter into your body. And the other reason you'll take the polyphenols, because they are the activators of a key enzyme in your body called AMP kinase. Little studies we've done in our laboratory show that we can take of cells, we can make them inflamed by activating with tumor necrosis factor, and as you add increasing levels of polyphenols, you can reduce the inflammation or reduce the activation of nuclear factor kappa B just by increasing the intake of polyphenols. And this is another thing we've done in our laboratory, demonstrating that as you add more polyphenols to cell cultures, you get more AMP kinase. Why is that important? Because AMP kinase is a powerful energy sensor. Polyphenols can interact directly with the genetic transcription factor SIRT1. This is the same factor that's activated by calorie restriction. Take enough polyphenols, you can activate that transcription factor, and that will cause the increased production of AMP kinase, which acts as a kind of a master switch for metabolism. We talked about that metabolism hormonally is in many ways controlled by insulin, but insulin's partner in this whole metabolic control is AMP kinase. And AMP kinase can turn on and turn off a wide number of metabolic functions, which can be basically critically important in maintaining survival of the species. So in many ways, as we're entering now the 21st century, we can now begin to look at diet not as a source of calories, but as a form of gene therapy. We can think of diet as really gene silencing biotechnology. Here are the inflammatory genes. They lie in every cell in our body. They haven't changed for hundreds of millions of years. They can be turned on and turned off by microbes, injuries, or our diet. The most powerful tool you have to turn them off is the zone diet, because it's an anti-inflammatory diet. Add omega-3 fatty acid levels, adequate levels, you get even more of a silencing of those genes, and add polyphenols, you get another layer of silencing. When you put these all together, you have a very, very powerful form of gene therapy to reverse insulin resistance, because you're silencing the inflammatory genes that cause insulin resistance in the first place. So if our goal is to reverse insulin resistance, and it should be, that means you have to follow an anti-inflammatory diet, not for a week, not for a month, but for the rest of your life. It means you eat small meals throughout the day. That's only possible if you're never hungry between meals. You need to have some protein at every meal. It's protein that gives rise to satiety. You need to eat primarily low glycemic load carbohydrates, that means primarily vegetables with limited amounts of fruit. Really restrict the intake of omega-6 fatty acids, which means you really want to prepare most of the meals yourself, and take high-dose fish oil to act as the ultimate dietary insurance policy. So if you do that, then I think in many ways, I've always said that we've made medicine more complex than it really is. It's like an iceberg. We see the tips of the iceberg, but the mass of the iceberg lies below the surface. And medicine is like the same. We see the iceberg. We see the cancer. We see the autoimmune diseases. We see aging. We see neurological problems. We see heart disease. But below the surface, they're all linked together. I believe all linked together by increased cellular inflammation. Cellular inflammation that can be reversed, and reversed in 30 days by the diet. But like any drug, that diet will only work if it's continued for a lifetime. So if we're able to reverse that, then we really have to be looking to controlling cellular inflammation, which means we have to retake control of our hormones, especially the hormones that cause inflammation. Diet will be the primary drug, and high-dose fish oil will be a key component of that diet. And if you're successful, it marks the beginnings of the return to modern medicine, when Hippocrates said, "Let food be your medicine, let medicine be your food." That was said some 2,500 years ago. Now we know what the old guy was talking about. He was talking about how food can affect our hormones, and how those hormones can turn on or turn off our genes, and if we're successful, we can live a longer and better life. If we ignore the power of food to alter gene expression, then what you see today in America is what you'll get tomorrow, but basically at a far greater intensity. And that is a outcome that no one is looking for. And so as a final summary, in my view, it's toxic fat that starts the development of inflammation in the adipose tissue. It's that inflammation that drives insulin resistance. And as the insulin resistance picks up steam, now lipotoxicity is spread to other tissues. And therefore, reduction of toxic fat is a necessary first step we have to reduce insulin resistance. If we ignore that, the future of our entire healthcare system is in peril, and unfortunately, the clock is running very, very quickly. And I think that's it. So with that, I'll turn it back to David and be happy to answer any questions that you may have.